I gotta choose for you. I can. So let's do this first. These are review questions, as you can probably tell, before we hit differential rate laws. Based on the reaction above, how many moles of electrons would be transferred for each? Go. Don't say it yet, or you probably want to do some writing. Or you can kind of think about it. All right, I'm going to give you 5 more seconds. Josh, what you got for me?
C.
Why do you say that? C is not the best answer.
Alright.
Han, give me what you got.
I thought it was C too.
Why?
Because it was -1 to 2 plus.
But that is the charge of permanganate and the charge of manganese 2+. Charges are not oxidation states. Remember that? Oxidation states are determining how many electrons are going to be transferred because it's redox. It's oxidation reduction, removing an addition of electrons. Lewis, tell me what you got.
E.
E? Thank you. I was glad you said B. Okay, so if you look at 5 electrons being transferred, you can see it from iron to iron, iron 2 to iron 3. 1 electron was transferred from the oxidation state of 2 to the oxidation state of 3, but there were 5 of them, so that means 5 electrons were transferred. Just be sure, though, that the other one is, let's see, permanganate. What's the oxidation state of manganese and permanganate here? 7 plus to 2 plus, so that's going to be a transfer of 5 electrons as well. So you really didn't have a whole lot there, but thinking back about how to do oxidation reduction is good. Which of the following is a strong acid? Chelsea. Ooh, strong acids. See? No. Diamond. I don't know this. Lies, Jack. Thank you. Perchloric acid. Tell me the 6 strong acids. Perchloric acid.
Hydrobromic, hydroiodic, hyperchlorite.
Good morning, teachers. Just a quick reminder that there will be a staff development in the media center. The first 10 minutes of each planning period, with the first one starting at 7:25.
What is wrong with my smartboard? Oh, it's plugged in. Oh, that makes sense. Where do you plug in at? All right, so we know that C is because it's one of the 6 strong acids. You gotta know your 6 strong acids. Just give me a second. Technical assistance required. How does this USB fit in here? There we go. Okay. This is nonsense. Green. Okay, we're gonna have problems today. I'm gonna fix this.
Oh, it's
Okay.
green.
Yes. Okay. How many liters? How many liters of 5 molar nitric acid are needed to make 5 liters of 2.5 molar nitric acid? Think about how you would do it. I see some people writing. Clayton, what you got?
E.
Why?
Because it's double the molarity in the first one, so you use half the liters to get to half the molarity.
Right, so you're going from 5 molar to 2.5 molar, so that's requiring half of the concentrated solution. But what equation are you using?
Molarity.
Yeah, M1V1 equals M2V2. Well, this is M1. V1, don't know. M2, V2. Well, if those two numbers are the same, then you're going to have 2.5 on this side as well, so 2.5 liters is good. Okay, keep it up here. According to the following, or sorry, identify the following reaction as something. All right, Nick, what you think?
It's B.
B, right. How do you know?
Because of the OH ion.
Just because the OH ion is there does not necessarily mean it's acid-base. There's more to it. Jack?
Because there's OH and an acid,
So what is the acid doing?
it's transferring the H plus to the OH to make them water.
Right, so basically, you know it's an acid-base reaction. If you see the donation of an H+, remember bad acids, rancid acids are donors. So if you see that Just the only change is a transition of a hydrogen ion, then that will be acid base. So yeah, you're right, because there's a hydroxide, but there's more to it. Okay, I'm doing this because I need to decide on some things, because we together, we're just, I think, 2 days behind from last year. I want to make sure we have enough time to review for our midterm in January, and then for the big boy in May. So there's a take-home test I usually give after the Q1. I did not give it because we were a little bit behind, and I was trying to overload you guys on work. But we're not going to finish kinetics before Thanksgiving break. So I have two choices. Either I can give you the kinetics test the day we get back from break, which kind of sucks. It could be good, it could be bad. I don't know about what you guys are doing over break. And I can give you the take-home cumulative test over break. Or I can give you kinetics test over break because it's fresh, it's there, and then the take-home in class the day we get back. The take-home is a cumulative test from units 1 through 5. So,
Wait, so.
yeah. So, I mean, that's a lot of work though. At home, 2 take-home tests would be really time-consuming.
I think the cumulative one, I'd rather be able to take home.
That's what I thought, but I
Because
didn't want to.
I can use things if I don't remember.
Yeah, and I would try to make it as manageable as possible, not too lengthy, because I just have to pick my battles, and which is the most important question sent home. So either take home cumulative goes home with you every break, and kinetics the day you get back. I can try to push kinetics another day, but that means I have to lose a day in equilibrium, which you're going to want. Okay? But we can kind of make that decision as we go throughout the week, okay? So just keep that in mind. I don't want a decision right now. Let's see how good we are with kinetics before we make that final call. I'm just putting it out there for you, okay? That's what I just need some joint decision there. Okay. All screwed up. You guys all screwed up yet?
I'm all messed up.
Okay. Look at your all screwed up stuff. Tell me what we think here, because this is going to give us some relevance to talk about in today's notes with rate laws. So, on your round 1, what were your R-squared values?
0.994.
0.994. Give me more. 0.988. More. I have 5 groups. 0.9834. 0.976. 0.9941. Okay. What does the R-squared value tell you?
How linear it is.
How linear it is. Okay. You've got to know how to use that stat plot. Please pay attention. You got to make sure you know how to use your stat plot in your calculator. How do you calculate R-squared in your calculator? And what does the R-squared value mean? It just basically tells you linearity. And if things are linear, what do you know about their relationship? Okay, yes, that is true for this particular example, but not for every example. So if things are linear, that means that they are directly related. Right? They have a good correlation, meaning they have a good relationship. It's usually a direct relationship. It depends on if it's a positive correlation or a negative correlation, but they are directly related to one another in some way. So what are the conclusions you can make about how the concentration of the reactant controls the rate of reaction? In this particular example, this was that one where you had the bolts and the screws, and you basically just had to screw them on. What was the rate determining step?
Proper orientation.
Huh?
Finding the proper orientation.
So the manipulation part where you're trying to find the correct orientation, that was the slowest step. So that determined the overall rate of the reaction, or how fast you could proceed, right? So how does this correlate to collision theory? I think we already talked about this. It's just correct orientation. Okay. This is not everything I'm doing. Just to show you some other stuff. So during round 2, what was your rate determining step? Getting the right nut versus the one that was too small or too big, or whichever one it was. Okay, so what happened to the concentration of the correct nut as you proceeded through the reaction? It went down. So what happened to your rate of reaction as you proceeded? It got longer and longer and longer. What happened to the slope of your graph? So what's that? So it went from steep, fast reaction to slower, some less steep. Okay, and it eventually levels off, and leveling off would indicate equilibrium. The R-squared values for that round 2 were what? 0.92. Give me more.
8.5.
That's what I'm looking for. Look at this correlation, or the correlation is going down, meaning the linearity is going down. More.
0.95. Sorry.
0.95. Okay. Point what? 0.97. Some of us had more correlation. Okay, this is more along the lines of what you're looking for. Because this one, we know the graph is not linear. We know it's got that little slope where it goes down, down, down. So this should indicate to you, between the differences between the two of these, you should say, does concentration of the correct nut have an impact on the rate of this reaction around 1? The concentration of the correct nut have a effect on the rate of the reaction around 1? Huh? Why are you saying no, Shannon? So there is no concentration decrease. It's going to be there. It's not like you're finding it in a stack of hay where you've got a heterogeneous mix. So the concentration of that particular nut had 0 effect on the rate. What had an effect on the rate? Huh? Yeah, you picking it up and oriented it the correct way. So if the concentration does not impact the rate of reaction, what order reaction is that? 0 order. Okay, so 0 order is something we're going to talk about more today. But how does that look on a graph? On your graph, I'm going to draw it really small here. Concentration versus, was yours concentration versus time on your graph? Okay. Concentration versus time. It should have been kind of like a straight line. Okay, so it doesn't matter what happens to the concentration. The rate does not change. Now, what is rate on here? Slope. The slope is constant. If the slope is constant, the rate is not changing. So it doesn't matter where I'm at in concentration, the rate is the same. And that's why the correlation was so close to 1, because of that concentration not affecting the rate. Now the next one was different. The next one had us looking at concentration, because you told me what happened to the rate as the reaction proceeded. What happened to the rate as the reaction proceeded? So the slope got more or less steep, but what happened to the rate? Slowed down, which is correlating with the tangent line or slope getting less steep. So concentration versus time on this one should have had a little bit more of a wiggle or a curvature to it. So the rate decreases, and that's correlating with a decrease in the slope steepness. So, question, does the concentration of the nut affect the rate of the reaction? The correct nut. Yes, because as you were fiddling around and trying to find the correct one, it slowed you down. So that means that the concentration of the correct nut did directly relate to the rate. So this one actually is first order. First order because the concentration does have an impact, and it was pretty much a direct impact. Like every time if you half the concentration from 10 correct nuts to 5 correct nuts, the rate probably doubled, depending on what we talked about. But this one's difficult to tell just from conceptual purposes. It's just knowing that it does impact it, therefore it does have an order, first or second. Okay, so that's what we're going to talk about today. So hold your graphs and I already talked about all this. Hold that. I'm gonna get back into presentation problems. I've been kind of neglecting that because we run out of time with that whole 80-minute period. These are things I'm going to probably have you guys do. I haven't fully decided on exact ones, but if you are here, I will have you present something this unit. Even if you get it wrong, I want you to be able to verbalize what we're talking about. Okay. Hold any questions right now. Let's go into notes. There is a one slide of note or one page of notes in your packet. It's page 2. Okay, we'll get to page 2. We'll probably get to page 2 through 10 today. That is page 2 through 6 today. We'll probably get to huh? 2 through 10. There's just some problems and some graphs. If you look at page 7, 8, 9, and 10, they're just a bunch of graphs. So we're really going to be talking about graphical analysis, data collection techniques, and how to read data from a table specifically today. And if you did a good job in your outline, then this will make a lot of sense. Okay, so who's in calculus? Woo! We've heard of derivatives and integrals. Yes? Okay, so we are not really going to be doing derivatives and integrals, but everything we do does relate to derivatives and integrals. And this is something that you can tell your calculus teacher, like, hey, we're doing relative rate laws. Okay, so they are actually called differential rate laws, but we just call them rate laws. Okay, so a rate law is going to compare concentration of a reactant to the rate of the reaction. So I'm just want to make sure that we're all clear that we're talking about concentration of reactants and not products, because products is going to be something we really hone in on in equilibrium, which is our next unit. So get right now in your head, kinetics deals with rates in comparison to the concentration of reactants. And so in our example from last week, some of those reactants were more important in determining the rate of the reaction. So in round two of your simulation, what were the two reactants?
The
Screw, nut, and the nut.
Okay, the screw and the correct nut. Okay, which of those was more important in determining the rate of the reaction?
correct.
The correct nut. So this one might be the only thing involved in controlling the rate of the reaction. Yeah, the screw was a reactant, so your reaction may have been screw plus nut equals product, but the nut was the one that was important in determining the rate of the reaction. So how would that be reflected in a rate law? That we would have to get some more experimental data from, but it would be rate is equal to K, which is a lowercase k, times concentration of the nut to some power, x power. So you'll notice that, yes, I'm concerned about the reactants, but I'm actually not concerned with both reactants. I'm concerned about the one that's controlling the rate. So that's where we're going to use data, graphs, and lab data that we collect to actually figure out the rate law. So rate laws are written like this. Rate is equal to lowercase k times concentration of a reactant, or maybe both, to some power. Yeah.
How are we supposed to determine what K is?
We are going to in just a second. We have to have data. So we can't just make stuff up. We have to have experimental data to support our thoughts. So everything will be given in a table or given from like a lab scenario. I'll show you data tables in a second.
Okay, because that was one of the questions on the lab.
Oh, well, you would have experimental data, and you would find the experimental data would have the rate, and it would have the concentration that you used, and you would find K because the X part would actually be known. So you'd have three variables. You'd have three variables, one of which was unknown.
Okay.
So I'll show you some data in a second there. So we're really concerned about concentration versus rate. Okay, so in this reaction here, I just want to talk about like some of the verbiage behind the scenes here, the lingo we used. Whenever we write a rate law, it is dependent upon the reaction and the reactant. So you'll see that I put rate is equal to K, which is called the rate law constant, times concentration. Remember, brackets mean molarity. Concentration of A to the X power and B to the Y power. But sometimes both reactants are important, sometimes one of them are important, sometimes neither of them are important. It depends on something else, like maybe the presence of a catalyst, or simply because there's something related to like half-life, which we'll talk about later. So these two, X and Y, those are called orders. So I don't say X power, I say to the X order at this point for kinetics. And we cannot just assume what they are. A lot of times people make a mistake and they'll say, oh, X and Y are 1 and 1 because of the coefficients in the reaction. That's called molecularity, and we will really talk about molecularity more later. The molecularity of the reaction is based off the BCE. So remember last week when we did relative rates, we were like, oh, A disappears twice as fast as C is formed if it had a 2 coefficient. So that's the relative rate, that's like the discussion of the rate. This is experimentally determined rate laws, so we have to have data to figure out these orders. So the 1 and 1 is called the molecularity of the reaction. The X and Y are called the orders of the reaction. So, second thing that I just need to note before we go. The rate law constant is something that you also get experimentally. But, give me a thought here. If I have a large K, what does it tell me about the rate? Or how does it correlate to the rate? Also larger, right? These are directly related. Increasing the constant would increase the rate. So if you only knew the constant, the rate law constant, you would also know something about the rate. You'd be like, oh, it's fast. It's, 10 times 10 to the 10th. So it's a fast rate, or it's a slow rate based off the size of this K value. And most of the time, whenever you have a large K rate law constant, it's because the temperature is also high. Okay? So the little k, rate law constant, is temperature dependent. That's something that AP exam will ask you about. It'll be an easy multiple choice question to get correct if you know that. So I just said they're not coefficients because that's called molecularity. And then I don't think I need really saying much else here. Let's talk about data. Okay, you're forward. Okay. So before we talk about data, in kinetics there are 3 big concepts we talk about. Just the relative rates, differential, and integrated rates. Integrated rates, I'm going to skip down to the second bullet here. Integrated rates actually talk about time as a variable. We know time is a variable here, but we don't specify time. We talk about time in terms of rate, because what are the units for rate again? Rate, like on the way to school. On the way to school, what's your rate? Miles per hour, but in chemistry, what's our rate?
Concentration over time.
Right, concentration change over the change in time. So this time is kind of embedded in the rate information itself, but the concentration and the rate would be two columns in a data table, and that would be given to you. Like that information is very explicit. Integrated rate laws, which we'll talk about more tomorrow and Wednesday, is going to be concentration, so that's one of our columns in a data table, and then time. But could we get rate from that? Could we get rate from that? How? Concentration over time, aka the slope. Okay, so you can get rate from other data. Specifically, it gives it to us in the differential rate law, but we find it ourselves in the integrated rate law. And this one's written very differently. Rate laws for differential are rate is equal to K times the concentration of A. I'm just making that my generic one, to the X power. Integrated rate laws are written like this. Concentration of A final is equal to concentration of A initial minus KT. Something like that. So they look very differently, and the time is in the rate law itself. So we'll talk about that one more tomorrow. And whenever we talk about rate laws, we are only indicating the initial rate, and we never say initial rate. You'll see that a couple times in your problem sets. But because after things start reacting, everything gets a little messy, equilibrium starts to become a factor, and so then we can't really have a standard rate that everybody's concerned about. We're really honing in to make sure we're consistent. We're honing in on the initial rate. And then rate laws do give us information about the mechanism of a reaction. And so in your guys's, I'll scroll back up, sorry. In y'all's lab you did Friday, what was the mechanism? What were the steps you took in part A, in round one? Tell me like 3 or 4 steps you took to accomplish your reaction. Pick up, screw, and tap. Step 1.
Screw.
Orient them. Step 2.
Screw.
Turn wrist to screw on part 3, continuing to part 4, right? So it's like a 4-step reaction. Which of those is the rate determining step though? Orientation. So the rate law gives us information about the mechanism because it tells us the step that is the slowest. It specifies that one. So the mechanism is going to be a step-by-step process, and we'll really talk about those more in depth later. But I just want you to know that it does give us information about the steps it takes. Okay, this is, oh yeah.
I was trying to write and listen at the same time, but it wasn't working. What is the A of F thing?
That's something we'll really talk about more later, but this is this is what an integrated rate law looks like versus what we are talking about today, what a differential rate law looks like. So I won't say differential anymore though, I'm just going to go rate law, and this one I will call integrated rate law because it talks about the time component. But we really will get in depth on that one tomorrow. Let's hit the first one. This is on y'all's sheet, okay? So this is just background information first before we start deriving our rate laws. So if I have this amazing reaction, what kind of reaction does this look like? Of all the types of reactions we know, is it acid base? Is it double replacement? Single combustion? So what kind of reaction is this? Redox, right? So this is just a redox reaction, and I'm giving you the 3 reactants indicated in the reaction itself, and then I'm telling you the rate law. The exponents for these are 1, 1, and 2. So what does 1, 1, and 2 mean? 1 means first order. 2 means second order. And so these exponents are just indicating the order of the reaction in respect to that reactant in particular. So what are these? I know this is really hard, guys. What's the order with respect to that thing? First order. Next one. First order. Second order. Overall order. 4. You just add them together. The order of the overall reaction is 2 + 1 + 1, which is 4th order. Okay, so then your job is to tell me how did the orders of the reaction, or how does that change in concentration affect the rate of the reaction? So the rate is equal to these things in their brackets, their molarities, to some power, to some order. So tell me, if I double the concentration of hydrogen, multiply that by 2, it's raised to what power? 1. So how would that impact the rate?
Double.
It would also double, because if I'm doubling the concentration of the hydrogen ion, well, 2 to the first power is just 2. So that is directly related to the rate, so the rate would also be doubled. It would be times by 2. It's this one, just because it's to the first power, so 2 to the first is equal to 2 is basically what we're saying here. So then tell me the next one. So bisulfite ion. That one is, let's see, double this one, HSO3. So the concentration would be given to you. I'm just writing it real dumb-like and putting times 2 inside the parentheses. So if I multiply that one times 2, what power is it raised to?
2.
2. So then how would that affect the rate? It would be 4. Why? Right. So if I double the concentration of this reactant, it's more important to the rate because it's to the second order, or it is the second order, so it's to the second power. So 2 to the second power would cause the rate to quadruple. And so it really is dependent upon the concentration. How do we manipulate the concentration, and what does that do to the rate of the reaction? Though it does depend upon its order of in reference to the whole shebang. So I just want to make sure you notice that these coefficients are not the orders. So that's one big mistake. People think the coefficients are the orders. They are not. These things had to be experimentally decided upon, which we'll get to in a second. Oh, let me actually ask you this one. So if something was third order, okay? No, let's say, yeah. If something was third order, what would happen to the rate if I doubled the concentration of that particular reactant? So if I'm just making sure, you say concentration times 2, and the reactant is to the third order, how do you get times 8? 2 to the third power. So 2 times 2 is 4, times 2 is 8. To make sure we didn't think that was 6. Okay, and then if something was to the second order, but the concentration was tripled, what would happen to the rate overall? Okay, so the concentration, what I just say, was tripled, and it's to the second order. That would be 9 times higher, so the rate would be to the 9, or multiplied by 9. Okay, cool. Let's talk about constants here. Do I have anything else down here? Oh, these are just ways that you would see how the rates should be written, and so immediately you should identify if it's second order, first order, zero order, and whatnot. The only one that we've not really noted is rate to the if the concentration is to the 0 order. How else can you write that? Well, a to 0 power is equal to what? 1. So anything to the 0th power is equal to 1. So a lot of times we can just cancel that out and not write that. So the rate is just equal to k. So if I ask for k for a 0 order reaction, then that also is just telling us the rate, which is also just telling us the slope. So if something was written like this, it's a little bit more complex, but we can figure out a lot of information about it. It's second order with respect to A, it's first order with respect to B, it's third order overall. Both reactants are important, but does that tell you every reactant there necessarily? I could have had something to the 0 power and just not write it, because like I said, to the 0 power is just 1. So these are the different ways things can look. Thumbs up when you get here. I'm trying not to do this thing where you get sick in November. I saw people walking around with like mask on at Walmart. I was like, I don't know, is that serious? Maybe it is, I'm not sure. Okie dokie. Alright, so this one, oh, no, sorry. People, I want to go directly to the data. Let's talk about K a little bit more. K has really interesting units. We should write our units every single time so we do not get the units for K wrong, because on the FRQ, they actually will say, what is the K? And if you don't have your units right, you get 0 credit. So if I know the concentration, if I know the rate units are whatever what again? Rate. Okay, so I'm just going to put molarity, just for easiness sake, molarity over seconds. Okay? And I know this information about the rate is first order. Well, what is the unit for A? Molarity, okay? Concentration means molarity. So what does the unit for K have to be?
Over seconds.
Over second, right? So I know K units are 1 over second. What's another way to write that?
Seconds.
Seconds to the -1. Okay, so you should be able to think about what are the K units based on the relationship that if it's first order, second order, 0 order. So what would the K units or the rate law constant units be for a 0 order reaction? So you can write it out. Rate is equal to K. So then what are the units for K?
Molarity per second.
Right, K is equal to molarity per second because there's nothing else to make the rate molarity per second except for K, so they have to be the same units. They have to be in agreement. Okay, so then what about second order reaction? Go ahead and write down some of these. I'll go back up here in just a second. I just want to talk about the units first. So try to find the one that what the K constant units would be for a second order reaction. So a lot of times if you just write down the general equation and start plugging in the knowns, then you'll figure it out. So rate is molarity per second. K is I don't know. A is molarity, but it's squared, right? So molarity squared. How do we get molarity squared to equal molarity per second? What does K have to be? Okay, so this would have to be 1 over molarity times seconds. Do you see why? One of the molarities here from the molarity squared has to cancel to leave us with only one molarity. So that's why I have to have a molarity in the denominator. And then seconds also has to be in the denominator because it's per second. So this can be written as 1 over molarity per second, or how else? Okay, give me one more variety. Remembering what molarity is, what's another way to write this? So in this case, if molarity is in the bottom, it's 1 over mole over liter. So then what happens to liter?
Goes on time.
Right, floppy dop, whatever. So liter over moles times seconds, or liter times mole to -1 second to the -1. They will write it in many ways. So I just want to make sure you're familiar with how to rearrange those if needed. And I'm going to scroll back up to the top in just a second to talk about what does K mean. So we already know K is the rate law constant. It is constant for a particular reaction. It's not a constant like the speed of light is a constant. It's true for everything. It's a constant for that reaction. And if the little k is a big number, what do you know about the rate?
Large.
It's a fast reaction, right? So if it's a large K, it's a fast reaction. But it's dependent upon time. It's dependent upon temperature, types of reactants. Are they ionic? Because ionic things are really difficult to break. And some other like surface area. It depends on quite a few things. So these are a couple things of what K is dependent upon. Specifically temperature, that's the one we definitely need to know. But like the surface area part is also going to help us speed up the reaction. So K is dependent upon the surface area, stuff like that. So, and this do not memorize the units for K. See, we just figured them out. You can figure them out every single time. You got brain space, things that are accessible. This is not something you need to memorize. Side note. Which of these is the most common? It's first order, and we will see that one most definitely whenever we talk about like radioactive half-life, first order reactions. A lot of times we'll see zero order sometimes, but it's not very common in the real world. And then specifically, second order reactions are more definitely going to be talking about things that are all in a gas phase or homogeneous gas phase reactions. Okay, now we're going to do questions. Okay, so this is called table logic. The way you figure out the rate of this reaction is called table logic. You saw this in the reading a little bit. Okay, so right on the table that you guys have in front of you, it's on like page 2. You find it? Make sure it's just right. Okay, cool. So here's how you do it. Whenever you're trying to find the rate of a reaction, they will give you experimental data. Experimental data looks like this, and you'll see its concentration of 2 reactants and then the rate of that reaction as well with these given conditions. So what you do is to have a controlled experiment, you always keep one variable constant, right? And you change one variable so you can see the impact of it. So in my first, between experimental trials 1 and 2, you'll see that B stayed constant. So I always just draw a straight line to indicate that those are constant. But what happened to the concentration of A? From trial 1, right, it doubled. So 0.1 molar to 0.2 molar means it doubled. So then how did that impact the rate? It also doubled. Okay, so if I double the concentration of A and the rate doubles, what order is A? First order. So A, so you know the rate is equal to K, A to some power, and then B to some power. And so I usually write the rate law at first just to indicate both my reactants. And then I just figured out A was to the first power, so I'm going to put a 1 there. so I don't lose that information. And it's only because 2 to the x power is equal to 2. Well, then what does x have to be? 1. So, you can do your mathematics and continue to prove it to yourself. Okay, so then what trials allows for A to stay constant but B to change? Pick your poison here. Which one?
3 and 4.
3 and 4. So 3 and 4 has A staying constant at 0.3 molar, and B, what? Doubling. Okay, then what happens to rate when B doubles? Quadruples. Okay, so B concentration is doubling. B is raised to, I'm going to call it raised to the y power. What does y have to be to equal 4? 2. So 2 squared is 4. So the rate of B is 2. The order of B is 2. Table logic is really logical. It's really nice whenever you have things that are constant. If you don't have things that are constant, you have to do this ugly algebra method, which is really, really quite easy. It's just still a bit more writing, but it uses more mathematical concepts. So there's our rate law, guys. That's how easy it was. But you cannot make this crap up. It has to be from experimental data, and that's why we always have so many tables and graphs and kinetics, because it has to be from experimental data. Okay, so now that I know the orders are 1 and 2, how do I find K? All I do is I pick one trial, use that information, plug in the information, solve for K. So let's just choose trial 1 if that's okay. Okay, trial 1. So rate is equal to K, A to the first and B to the second. So what is rate of trial 1? 0.2 molar per second. 0.2 molar per second. I'm actually going to just go ahead and solve for K in variables here. So I'm just going to divide by A to the first, B to the second. So what's the concentration of A in this one? You guys have the data in front of you. Thank you. 0.10 molar to the first, and then B.
0.1.
Okay, this equals K. What is that? You guys have your calculators out. Or you probably can maybe do it in your head. 0.2. That's 2. So what's 2 over? 200? Okay, so that's the number, but that's K's magnitude is 200. What are K's units? What is K's units? What cancels over here?
One of them.
One of the molarities on top and bottom. That's it. So what are the units?
1 over second.
Seconds squared, right?
Second squared.
So the seconds comes down to the denominator, and there's already a molar squared in the denominator, so the units are per molarity squared seconds. I generally write molarity first, but that's why you'll see that. And then tell me, does this make sense? Overall, this reaction was what order? Third order. And if it's third order, you've got rate is equal to K times something to the third. I know they're different things, but still, it's just molarity to the third power. So then you have to cancel out 2 molarities to get it down to molar per second. So that's why there's 2 molarities in the bottom, or molarity squared in the bottom. Cool? How are we doing? Dead to the world on a Monday. But help me out here. Do we know how we got K? Shake your heads. I see like 3 people. Okay. All right, so then you guys tell me what this actually, I need to do like one more example with you. No, we can do this one. Let's do table logic here. Table logic. Tell me where you're starting.
First 2 trials, B is constant.
Okay, so in the first 2 trials, B is constant. And then what else? A is doubling. So this is just how I indicate it on the chart itself to keep track of my numbers. Okay, so if A is doubling, what's happening to the rate? So no change. So then what did you say?
0.
A is 0 order. So rate is equal to K, a weird looking K, A, B. A is to the 0 order. Because you just told me the changing of the basically what you said is conceptually, changing the concentration of A has no impact on rate. If you have no impact on rate, you don't matter, you are 0 order. Okay, so we got A figured out. How do you figure out B?
1 over
So from trials 1 to 3, what's happening to A? Okay, so that's our constant. From trials 1 to 3, A staying constant, and what's happening to B? Is that in my room?
No.
Okay. Okay. Cool. So B is doubling here in concentration. What's happening to the rate? You see, it's quadrupling because you're at 7 to the -5th here, and then 28 to the -5th. Really, so 7 to 28 is times 4. The decimal changes on you here. So that's times 4. So then what is B? Right, so basically, if you're multiplying by 2, it's to some power, and that power has to be 2 to equal 4. So then this is a second order reaction overall. So we did figure that out with table logic. I want to prove to you how this works the same way with ugly algebra method. And ugly algebra method is going to be something you use whenever something is not constant in the table, so you can't do table logic. Okay, it's your second go-to. Yeah?
If A wasn't 0, would the 2 coefficients be?
No. It doesn't change anything regardless. It's just saying the molecularity of the reaction requires the recipe of 2 A's plus a B to yield 3 C's. It's just the recipe. It's the mole ratio. Okay, so ugly algebra method, how do you do this? You put rate over rate equals the rate laws. Okay, but I actually have that up for me. I'm doing rate 3 versus rate 1. Rate 3 versus rate 1 is how we figured out the rate or the order of B, right? So I'm basically showing how I would calculate B if I didn't see this constant nature here. So I'm going to put 3 over 1 because 3's rate is faster. It's a bigger number than A. And it's really helpful when you have a larger number on top and a smaller number on bottom. So rate 3 over 1. What was rate 3? 2.8 times 10 to the -4th molar per second. And rate 1 is 7.0 times 10 to the -5th molar per second. Okay? And then what do the rate laws equal? Would they equal the same format? What's the first thing in a rate law? K. Okay? Times the concentration of A to the 0 we had already figured out. And let's pretend we don't know B for a second because I'm just trying to prove this to you. I'm going to call it B to the X. So if we're comparing trial 1 to trial 2, the rates we actually can go ahead and simplify. What's 2.8 times 10 to the -4th over 7.8 times 10 to the -5th? 4. We'd already figured that out. Okay, what can we simplify here? Okay, so the A to the 0s can both be simplified because it doesn't matter the concentration we put in there, there's still 1. So those two things I'm actually going to just go ahead and cancel because they are the same. What else can I cancel? K, because K is a constant and it's same for all trials of the experiment for that particular reaction. So K's can also cancel. So really what am I stuck with? B to the X over B to the X, right? But this is for trial 3 and this is for trial 1. What was the concentration of B given in trial 3? 0.2 to some X power, okay? What is the concentration in trial 1 for B? 0.1. Okay, so math people, how do you solve for X in a situation where you have something like this? Logs. Okay, so we have to use logs to solve this, or natural logs, either way. Why are we using logs? Because basically when you multiply both or put log involved on both the left and the right side, the X is able to come down due to your log rules, right? The exponent comes down as a coefficient. So then you can isolate X and actually solve for X. Right now it's difficult to solve for X, but can we simplify this a little further? 2. So 0.2 over 0.1 is 2 to the X power. So you can simplify your numerator over denominator here to this. I know you can mathematically go like, oh, duh, X is 2, but I want to show you in a difficult situation where you could not. So then here's where you use your logs. So once you've simplified as best you can, then you put log, I need space, you'd have log of 4 is equal to log of 2 to the X. And then what do you do? Right, the X comes out to the front, so log of 4 is equal to X log of 2. And then what do you do? Right, you just pull log of 2 over, and simplify. So log 4 over log 2 is 2, and X is equal to 2. That cancels. So I know we easily could do it in table logic because our variables were able to stay constant. But this is called ugly algebra method just because it takes a little longer, but mathematically it's very sane, and you always get the right answer if you put the larger rate over the smaller rate. Okay? I'm gonna do like one or two more. You guys tell me what I need to do though. For this one, yeah, actually, you guys just start this by yourself. Okay? You have a partner next to you if you need help. This one spells out a lot to you at first. This one I'm gonna make on your notes.
This one?
All right, so I hope we all got the rate and is indicated from the description, second order and first order. Check here. Yep. Just remember to put your K. Oh, that's the thing. Most people do. They just forget to put the K there. Okay, so just be aware of that. The next one, you have defined the rate from given conditions. So K was given to us as blah, 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 molarity or over molarity squared seconds. And then these two concentrations were given to us respectively. So make sure you're just following the line to see which one is which. Everything should cancel except for what units? And one of the molarities, right? Because you'll see molarity squared will cancel with these molarity squared here, but one of the molarities will stay, which makes sense because rate should be molarity per second. What was y'all's answer?
1.5 times 10 to the -8.
Okay, molarity per second. All right, so that's the rate of the reaction with those concentrations. What is the rate when NO is doubled and hydrogen gas is unchanged? Do you have to plug this into a rate law? No, you can do it from concepts, right? So if nitrogen monoxide is doubled, what should happen to the rate?
Quadruple.
It should quadruple because if the NO is to the second power and you double it, it's actually doing 2 to the second, to the second power, which should quadruple. So then what should this be?
So it's 20 times.
Yeah, so 15 times 4 is 60, or 1.5 times 4 is 6.0, times 10 to the 8, negative 8 meters molar per second. I always say meters. So you actually didn't have to plug into anything except for think about how does the rate double, or what happens if the concentration doubles. Okay, last one with me. Next page. Next one for you guys. This information, determine the rate law constant. Specifically, I want to talk about these two, so quickly do 1 and 2 for me. Just because some of the phrasing of the questions are a little different. Keep doing it on your own paper. I'm going to do it up here. All right, so everybody get NO squared and then, or to the second order, and BR2 to the first order from table logic, yeah.
What about the 0.3?
So that one you couldn't account for because of the rate not being present in trial 4. So that we're going to talk about in the next step here. We're going to figure out what the rate is, and then we can verify that our orders are correct, but you just couldn't use that trial.
So what do you use to get the exponent?
So I used trial 2, 1 and 2 for the first one, because I said, color here. I said A state, or nitrogen monoxide stayed constant, and B, R2, doubled, and I saw that the rate doubled, so then that meant bromine was in first order. And then for the second identification, I did trials 1 and 3, and I saw that nitrogen monoxide doubled, their bromine was constant, and then the rate here quadrupled. So if you double and then you equal a quadruple rate, then that X has to be second order. So nitrogen monoxide was in second order. So once you got there, you had to plug in data from one of the trials to find the K, the rate law constant. So when I say rate law constant, you know you're finding K. So rate over the concentration of the reactants to their appropriate powers. K equals what, Kevin?
12,000 moles over molar squared seconds.
So 1.2 times 10 to the fourth per molar squared seconds. Okay, I like that scientific notation. Okay, so if we find K just from plugging in data, making sure we're plugging in our calculator correctly, what is the rate of appearance of NOBR? How would you do that? I'm not going to show the whole thing, but how would you do that? There's a better way. Plug it in. Plug it into what? Right. I know the rate law information in 100% now. So I would have K I would look at the table for concentration of nitrogen monoxide, and I'd look at the table for concentration of bromine, multiply those together, and I would get rate. So rate of trial 4 is just all that multiplied together with their appropriate exponents. And what'd you guys get? What did you get, Lewis? 108, yeah. 108 what? Molar per second. And that's, you guys saw, you just basically are plugging in K and then the concentrations and then figuring out what your rate is. Okay, so the last part is really what I want to get to in this whole thing. This one's kind of using the whole relative terminology we talked about last week, so appearance versus disappearance and then comparing the two. So what is the rate of disappearance of bromine when nitrogen monoxide is that and bromine is this? So when you see the disappearance of bromine, you're probably like, okay, well, I'm declining, I'm using that bromine, but how are our rates already expressed? You see how it's expressed? How? Appearance of the product of nitrogen or NOBR. So if we have the rates in reference to NOBR, how do we reference it back to bromine? Molecularity, the ratios, and that's what we did last week. So I just want to pull these two together for you. So first of all, what's the first thing you can? What's the only thing you can calculate here? The rate, and I'm going to say appearance of NOBR, just to remind us that this rate table is related to the appearance of NOBR. So then how would I get the rate? Well, I already have the K of 1.2 times 10 to the fourth molar per second. And then I would just plug in the values for the nitrogen monoxide squared, and then the bromine, is that one squared? Yeah, and then the bromine 0.185 molar. So then what is this rate? Anybody got me? 12.5 molar per second, right? Okay, so that's the rate of appearance of that product. So then how do you relate that back to the disappearance of bromine? Well, you can look at the ratios. What are the ratios between the two of them? What can you relatively say about this? Okay, so it declines at half the speed that NOBR is formed, or you can say NOBR is formed twice as fast as bromine is consumed. Use your kind of verbiage there. So what are you actually doing? You're actually doing a mole ratio. So that's the formation of NOBR, and then bromine, there's two bromines consumed. Oops, I'm sorry. Is that formation? There's two NOBRs produced for every one bromine, and so to cancel out the NOBRs, then you're going to get 1/2 the rate. So this would be 6.25 molar per second is the rate of disappearance of BR2. Just because of the ratio. Yeah. Okay, so I'm going to stop for a second. How are we doing? Can we get rates by ourselves? Can you prove it to me by looking at the problem set right below? We have about 30 minutes left. I think you'll get finished this first problem set. So I'm going to give you specific ones I want you to do. It's called Differential Rate Law Problem Set. It starts on page 3 in your packet. Highlight, do 1, 2, 4, and 6. 1, 2, 4, and 6. And then after that, I will tell you from the next section which ones you guys are going to be responsible for. Because there's graphs and there's data tables. I want you to try to look at both of them. I'll kind of pick and choose. So problem set, what did I say? 1, 2, 4, and 6. That should take you no more than 20 minutes maximum. Okay? Show your work on a separate sheet of paper for me, unless it's table logic, so you can do the little drawing the line thing. If there's math involved, please show it on a separate sheet of paper, unless you can legibly write it there for me. Table logic, I'll understand if you put a little line. Soon I'll show you what's expected in like the exam for work for this, because it's like you just show your work for this, but sometimes you just look at a table. So how do you show them that you did it? Is that a video?